And now we want to talk about how to classify environments. And we're going to use 8 different attributes for classifying different AI tasks: simulated, static, dynamic, discrete, and so on. And these are the definitions of those terms. But rather than just reading them out one by one, it's more helpful if we look at it in relation to a specific example. And the example we've chosen is comparing chess with Robocup soccer. Now, you're all familiar with chess. Chess is a board game where you move the pieces around the board and capture each other's pieces, and eventually you have to get the king in checkmate. There's no dice, no rolling of the dice, no shuffling of the cards. It's just moving of the pieces. Now, in the years from, say, 1958 until 1996, chess was a big driver of artificial intelligence and actually computer science in general. Arthur Samuels, working at IBM, started working on chess in the late 50s, chess and checkers. Donald Mickey worked on it in Britain in the 60s. And not just AI, but a lot of fundamental computer science techniques were actually driven by this push for computer chess, including hash tables and data compression, and also, of course, machine learning. And it was a big driver for faster computers and so on. But then in 1996, Deep Blue beat Kasparov. And then a group of researchers led by Hiroaki Kitano at Sony Computer Science Labs in Tokyo started having meetings and said, well, we need a new driver. You know, chess is done now. Chess is more or less solved. So we want to have a new task that will drive further research in computer science and drive the kind of research that we need in the modern era. And eventually they decided on robot soccer. And so that's where they founded this Robocup Soccer League, and we've been having these competitions every year since. Now, I'm sure you must have all seen videos of Robocup Soccer before, but let's just have a look at a little bit of video just to sort of remind ourselves. Good. Okay, so you get the idea. So the first thing is simulated versus situated and embodied. So simulated means that a separate program is used to simulate the environment, feed percepts to agents, evaluate performance, etc. Situated means the agent acts directly on the actual environment. Right, so you can see chess is simulated, whereas Robocup is both situated and embodied. So you can see the agents there with the robots that are acting directly on the physical environment, and they also have a physical presence in the world. We'll say a bit at the end about the difference between these two things, but both are true in this case. Now, you could ask, what do we mean by chess? What would happen if you had a physical board and you actually had a robot manipulating the pieces? Would it then become embodied? And the answer is yes, it would, but we normally abstract away the game itself and treat the movement of the pieces as a separate task. When you think about it, these two tasks are really quite distinct. You could assign one team of programmers to do the move selection and another team to design the thing that'll move the pieces, and really they would hardly have to talk. They wouldn't have to talk to each other at all. You know, it's two completely separate tasks virtually. And in fact, it's interesting, in Go, Rodney Brooks tried to do that for Go a couple of years ago. Just get a robot, not deciding the moves, but just a robot that can pick up the little stones and move them to another place. And it turns out to be actually quite hard to do that. But this is, way back, a friend of mine had one in 1981, I think it was. He had one of these early chess playing machines, and it did actually have a physical chessboard and it had a robot. So it was kind of cool to watch it. You know, you would make your move and then you'd have to sit for 3 minutes, 5 minutes while it decided its move, and then this arm would come out and pick up a piece and move it. But really, that arm was really just a gimmick to disguise the fact that actually it was a pretty poor chess player and took a long time to make its moves. You know, so, but it was cool to watch it. Okay, static versus dynamic. So static means that the environment doesn't change while the agent is thinking. Dynamic, the environment may change while the agent is thinking. So you see, if you're playing Robocup, you walk up to the ball and then your ball disappears. That's right, it's a trade-off. You might sit there and have lots and lots of processing. Oh, what am I going to do with this ball? Oh, I could kick it to my friend. Oh, where is my friend? You know, I could kick it to the goal. Oh, this is so exciting. But while you're thinking, another robot comes in and kicks it away from you, right? So the environment is, other robots are continuously moving around you. Chess, on the other hand, is static. Now, this is something some people get confused about. If you make a move, then obviously the opponent is going to make a move, right? So you're not the only agent affecting the environment. The opponent will move as well. But it's still considered static because while you're thinking about your move, you know that the environment won't change. That's why it's static. After you make your move, then the opponent can move. Now, the other thing, when we start to do these classifications, there's always these slight caveats and so on. So you couldn't literally sit there for 3 weeks to make your move. What happens is, like, as you're in tournament chess, while you're sitting there thinking, the chess clock will tick down, tick, 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 tick. So you could regard that as a slightly dynamic element in the environment, but it's very slight, very subtle. All right, the next one is discrete versus continuous. Discrete, only a finite or countable number of discrete percepts and actions. Continuous, the states, percepts, or actions can vary continuously. So in chess, you're not allowed to have a piece in between two squares. It has to be either on this square or on this square. That's why it's discrete. There's a discrete choice between this and this. Whereas in Robocup, of course, the ball and the robots their positions can vary continuously, and Robocup is actually continuous in time as well as in space. Chess is discrete both in time and in space. Fully versus partially observable. Fully observable means that percepts being fed to the agent contain all relevant information about the world, right? So if you're playing chess, you can see, or you're told, where all the pieces are on the board. And if necessary, whether the king has castled, or whether the king has moved, or whether a pawn has just been moved up. You're given all the relevant information that you need. relevant information. You don't know whether, you're not told whether your next door neighbour's back lawn was mowed last Thursday, so there's always more information that out there, but everything relevant to making your decision. Now you can see that, what about Robocup? Now this is where I got a couple of videos from the old days when they had four-legged robots instead of two-legged. And again, yeah, we don't think we have the sound here, but it's just, the motors crunching sort of thing. And we used to have these beacons, and so, the field was smaller, it had these ridges around and these beacons, but it was similar rules. I think that's illegal, but it might have been by accident. If you can claim that you're going towards the ball, it's allowed. Now this is interesting. So you see these robots are at the ball, but watch this guy here. This is very interesting. This guy's making his way around just in case he has an opportunity. He's a bit confused, but you see the ball comes out of the scrum and that guy's there ready to take advantage. Okay, very good, yes. Now, but this is what's really interesting. This is what the dog dog actually sees while it's playing. Oh. It's always interesting to see the agent's point of view. You see, this is actually one of the rare frames where we manage to see a beacon and the ball in the same frame. The color's a bit funny on this one, but the ball, there's a bit of orange there, which is actually the ball, and that's the beacon. So you have to rely on, I think it's worth seeing that again, you have to rely on these rare glimpses of these landmarks, and when you see a landmark, you remember that and try to use that to triangulate your position, and the same thing with the ball. Okay, so now is Robocup fully observable? No, so we call it partially observable. Now I should explain a little bit more about the rules. So that particular league, the robots are allowed to communicate with each other, but they're not allowed to communicate with an off-board server. So they may get some information from what the other robots are seeing, but they don't have the full information. It's often the case that and you saw when that guy was circling around looking for the ball, right? He didn't know where the ball was. So sometimes they don't know where the ball is, sometimes they don't know where they are on the field, and they certainly often don't know where the other robots are. Yep.
And about the game with Pits and
yeah, Wumpus, yeah.
Is it partially observable or fully observable? If it depends on our actions, how much we see.
Very good question. The question was, is Wumpus World partially observable or fully observable? Who says partially observable? Who says fully? From the player's perspective. It's actually partially observable. So a very good question. Wumpus World is partially observable because you don't, in a fully observable environment, you have all the relevant information when you need it, at the beginning essentially, right? So the Wumpus World, when you start the game, you don't know where the Wumpus is, right? But that would be very relevant information. You don't know where the pits are. Yeah. So it's partially observable. Yeah. Good question. And there are some variants of chess. There are some chess variants where like you can't see the other person's pieces or this or that. Then that makes it shadow chess or something. That would make it partially observable. But in the normal game, it's fully, yeah. Okay, now I want to show you another movie now, though this is this is a different league of Robocup. This is actually a team that a team I was involved in many years ago at the University of Melbourne. It's a bit of a shame we can't get the volume here, but if you look on the Open Learning side, you'll actually see the volume. Now, in this league, well, someone was asking about penalties. If you look closely, you'll see we've only got 4 robots on the field and the other team has 5. That's because one of our guys had a red card. He got sent off. And so one of our guys has to try to block 2. You see this, one of these guys here is actually going back and forth between these other 2 robots, because we're down a robot. But the main thing about this environment is that in this league you're allowed to have an overhead camera. That was the other thing. Sometimes the magic stick of the referee would come in just to liven things up a bit. The ball got stuck. Yeah, I mean, this league is, they don't have, they've expanded the field and taken away the barriers and so on. Like, it's very different now. But in this league, there's actually a camera hung above the field, and the camera sends its images to a, there we go. The camera sends its images to a desktop computer, and then the desktop communicates wirelessly with the robots. And we had a simulator, and we would run the software with the simulator, and then we'd run it with the real robots, and the behavior was almost the same. Of course, the simulator can never be quite as good as in reality, but because of the overhead camera, the robots do actually know the position of all each other and the ball to a pretty high precision. So we generally regard that league as being fully observable, right? So it's these questions about observability and so on really depends on the way the environment is set up and the specific rules and so on. So many distinctions. Now, okay, then deterministic and stochastic. Deterministic means that the current state uniquely determines the next. In chess, if I make a move, I know exactly what state the board is going to be in at the next move. But in Robocup, there's a certain random element. So we regard this as stochastic. Now, we'll talk in a minute. We'll talk about dice games and so on, where you've got explicit sort of randomness. But and this kind of gets sometimes into a bit of philosophy. Someone could object, well, if we happen to know all of the locations of the objects with high precision and so on, maybe we could predict the trajectory of the ball and so on. But in fact, that's really not well. So there's two issues here. So first of all, we treat it as being stochastic just because it's like we can never have complete information about the game. We can never know precisely whether the leg of the robot is hitting the ball here or here. So, and then it could have a big difference on which direction it goes. So the randomness partly comes from just the fact that we can't perfectly model the physics. But even if we could, the quantum mechanical effects at the quantum level would still make it stochastic.